In this section we'll talk about signal to noise ratio and noise figure. We are interested in deriving the signal to noise ratio at the input of the analog to digital converter based on the parameters and specifications of the RF analog front end. This diagram we show the block diagram of a OFDM receiver. We have the receive antenna and the radio and analog to digital converters. Usually there's a very tight interaction between the baseband digital signal processing over here and the RF front end. For example, automatic gain control, DC compensation, and IQ imbalance. However, in this section what we are interested in is, given the specifications and the parameters of the RF front end, what is the signal to noise ratio at the input of the ADC? The sensitivity of an OFDM receiver is impacted by the noise figure of the analog front end, which is one of the most important parameters in determining receiver performance. Once the, in our case, 0IF radio or direct conversion radio has converted the signal back to baseband and it has been sampled and converted to digital by the ADC, there are many processes within the digital baseband signal processor that can improve sensitivity. We've talked about some of these processes. For example, on the Viterbi decoder, you can use a larger traceback buffer. You can use 3 to 5 bits soft demapper. And in the case of equalization, you can be smarter about the way you do equalization and smooth, for example, the channel estimates. You can use higher precision in the FFT. For example, in acquisition, you can do a better job in timing synchronization and, of course, in carrier offset estimation and correction. However, the RF front end has a huge impact on the sensitivity and therefore the performance of the OFDM communication link. So in this section we will deal with the derivation of the signal noise ratio at the input of the A to D based on the parameters of the RF front end, and in particular we will focus on the noise figure. To begin, we need to define noise figure F. So if we have a block, which could be an amplifier, could be a lossy transmission line, it could be the mixer, for example, the path through the mixer, it could be an analog filter, for example. A particular analog block will have an input signal to noise ratio, SNRN, and an output signal to noise ratio. In all cases, an amplifier or a lossy component will add noise to the signal, therefore the signal to noise ratio will degrade. And the way we measure that degradation is through the noise figure, which is defined as the ratio of the input signal to noise ratio to the output signal to noise ratio. If we write the signal noise ratio in terms of the input signal power divided by the input noise power and also the output signal to noise ratio, if the block has a gain G, then the signal would be amplified by G, so you have G times the input signal divided by G times the input noise plus the input referred amplifier noise. So NAI is the amplifier noise referred to the input port. So we see that the signal to noise ratio would decrease as we go through the amplifier. If we go through this expression and cancel out SI and also G, we obtain the following expression for the noise figure. So the noise figure becomes 1 plus the amplifier noise referred to the input port divided by the input noise. And as you can see, it's always greater than 1. Therefore, there is always a degradation in going through an amplifier between the input signal to noise ratio and the output signal to noise ratio. The composite noise figure is obtained by when you have 2 stages, a first stage followed by a second stage. Each stage will have a gain G1 and G2, and each stage will have an associated noise figure for that stage, F1 and F2. Now, although we indicate gain, if G, the gain, is less than 1, then we are dealing with a lossy component. We can derive the expression for the composite noise figure, and we obtain the expression that it's equal to F of 1, the noise figure of the first stage, plus the ratio of F2 minus 1, the noise figure in the second stage, divided by the gain in the first stage. And this is a very important relationship. and shows that if we have gain in the first stage, then the noise figure of the second stage is divided by that gain, so it's reduced considerably, and also the noise figure of the first stage dominates. If we have multiple stages, as we will show, you might go through the lossy transmission line, a low noise amplifier, and also the mixer and baseband filtering, then you have multiple stages, and we have a famous formula for the noise figure for a cascade of stages. This expression here shows the importance of the gain at the front end. So G1 is the gain at the first stage, and the higher that gain is, then the less the overall noise figure for the system. As you can see, the gain appears in every single term in the denominator, and the higher the gain is, the less and less the contribution of the noise figure of the following stages. It also shows that no matter what you do, you are always bounded by the noise figure of the first stage, F1. Here we show the front end, RF front end for a direct conversion receiver, or 0IF or homodyne receiver. You have the antenna connected to the low noise amplifier, which we will discuss, through hopefully a low loss cable, which is as short as possible. The reason that this cable should be, first of all, very short, and second of all, have very low loss, is the fact that if you have loss in the first gain, the first stage, then G1 would be less than 0, then 1 over G1 is actually an amplification of all the noise in the rest of the chain. So it's imperative to have no loss or very little loss at the first stage of your receiver. And that's why, for example, you see in satellite antennas, especially in external satellite antennas, that the low noise amplifier is built right near the receiving antenna, and then the signal is amplified and sent through a long cable to the GPS receiver, for example. This is also used in microwave links, where right at the dish you have an LNA, and then you amplify the signal and send it through a lossy cable, maybe a long cable, to the actual demodulation processors. So let's focus on the analog front end as shown here, and we've simplified things a little bit. So the first stage, ignoring the loss through the cable for now, the first stage is the low noise amplifier, which we require to have high gain, G1, and a very low noise figure, because if this amplifier does not have a low noise figure, then a high noise figure at this stage will dominate, and the higher the noise figure, the worse the sensitivity of our overall OFDM receiver. So if we look at the total noise figure, we see that we need a low noise amplifier with a very low noise figure and a high gain, and then we can also go through the various stages. For example, the mixer usually has attenuation, and you have various gains within the receive chain and filtering going on, and all of those have high noise figures. But as this expression shows, the key is the noise figure of the LNA and the gain of the LNA. This is one reason why LNAs are external components, so they can be built from devices that have a low noise figure and a high gain. Recently, manufacturers have been able to build on-chip LNAs and achieve very good performance. We have shown some of those devices and introduced some of those vendors in this presentation. But that is the challenge. In order to improve sensitivity, sometimes you have to use external components, external LNAs. We will also introduce the concept of effective noise temperature. So if we look at the noise at the input of an amplifier, for example, N sub I, we can relate it to the effective noise temperature T sub I through the bandwidth and Boltzmann's constant. So the noise can be thought of as depending on the bandwidth, and through that the effective noise temperature T sub I through Boltzmann's constant. Also, the amplifier noise referred to the input can also be expressed in terms of an effective noise temperature through the bandwidth and Boltzmann's constant. So if we substitute for the expression for the noise figure of an amplifier, and we replace the noise with the effective noise temperatures, we can actually express the noise figure in terms of the ratio of the amplifier noise effective noise temperature divided by the input noise temperature. Also, there is a similar expression for the overall noise temperature of the system, and it depends on the noise temperature of the first stage and the gain at the first stage, and also the noise temperature of the following stages and their gains, similar to the previous expression. In the following, we need to define the one-sided noise spectral density. If we have white Gaussian noise, for example, then the power spectral density would be constant as a function of frequency. The power spectral density on each side would be N0 over 2. Or if you express the spectrum in terms of a one-sided spectrum, then the one-sided noise spectral density would be N sub 0. So that's what we mean by one-sided noise spectral density. We're actually referring to N0, and usually when we do system analysis, we deal with a two-sided spectrum and we deal with N0 over 2. Here we have the expression for the noise figure in terms of the effective noise temperature of the amplifier and the effective noise temperature at the input of the amplifier. When a noise figure of an LNA is specified, for example 2.4 dB, we need to calculate what the effective noise temperature is for that amplifier. So let's rearrange terms over here and derive T sub R in terms of the noise figure and T sub I. So here we have the expression. If we rearrange terms, then we get that TR equals F minus 1 times T sub I. Now the issue is, if we're given a noise figure, what is the effective noise temperature of the device? According to this equation, we need TI, the input noise temperature. The IEEE, as part of its definition of noise figure, has specified a reference temperature of 290 degrees Kelvin that we can consistently use in order to derive the noise temperature of a device from the noise figure. So in this case, we use 290 degrees Kelvin for T sub I, so we can calculate the effective noise temperature of the device from the noise figure using the reference temperature. Also, at the reference temperature, if we compute the one-sided noise power spectral density, according to this equation here, using the reference temperature, then we get that it's equal to a nice number, which is 4 times 10 to the minus 21 watts per hertz. So later on, we will actually use the expression T sub R equals F minus 1 times 290 degrees Kelvin in order to come up with the noise temperature based on the specification of the noise figure. The total system effective noise temperature can be computed as a sum of the noise temperature of the antenna noise temperature, plus the receiver noise temperature. And the received noise temperature is this expression over here, the overall noise temperature of the receiver. The antenna noise temperature could be, for example, 400 degrees Kelvin, and is the noise that is introduced into the effective noise of the receive antenna, and this number depends on many factors, but we'll give you some typical numbers. Of course, the T sub R is the total receiver noise temperature and includes loss from the antenna to the LNA, the mixer, and other losses throughout the system. Here's an example of a cascade of a system where we have a bandpass filter, the LNA, another filter, and we go through the mixer. And here's some parts for the LNA, and here are some specifications for the LNA. This is from IMEC, published in 2000. The LNA, for example, has a noise figure of 2.4 dB and a gain of 12.9 dB. The noise figure of the composite bandpass filter plus LNA plus bandpass filter is 5.4 dB. As you can see, it's increased compared to the noise figure of the LNA, and the overall gain has decreased going through the bandpass filter. If we add the mixer, and the noise figure has increased. But the point is that the mixer has increased the noise figure from 5.4 dB to 7.5 dB. Here we have the receiver performance requirements for 802.11a. Recall that At each data rate, like 54 megabits per second, the minimum sensitivity in dBm is the minimum input power level at which we achieve 10% packet error rate with a packet size of 1,000 bytes. So this is the minimum required sensitivity to meet the performance of 10% packet error rate with a packet size of 1,000 bytes at 54 megabits per second. Usually designs have to exceed this requirement in order to compete. Also shown is the minimum sensitivity at 6 megabits per second, which is at minus 82 dBm, and of course we expect the sensitivity much higher when we use 6 megabits per second. But we will use this table in order to derive the signal-to-noise ratio for OFDM in 802.11a. Also in the standard, note that they've used a noise figure of 10 dB with a 5 dB implementation margin. So we'll use the noise figure over here, although many products today far exceed the noise figure performance by actually having noise figures of 5 dB or 6 dB to improve sensitivity. But we'll use the 10 dB figure provided in the standard. So if we use a noise figure of 10 dB, and we know that the input power at 54 megabits per second at a 10% packet error rate with 1,000 bytes per packet is minus 65 dBm into 50 ohms. And what we're interested in is finding what the signal-to-noise ratio is at the input to the analog to digital converter. We also note that the bandwidth W is equal to 20 megahertz. Now, because of the guard intervals in the frequency domain, the nulls at the upper and lower parts of the spectrum in 802.11a, the actual bandwidth is 16.5 megahertz, for example, and we'll take that into consideration, but for now consider that the bandwidth is equal to 20 megahertz. Now we have the expression for the received noise, effective received noise temperature is equal to the noise figure minus 1 times 290 degrees Kelvin. Now, noise figure is usually expressed in dBs, so the total received effective noise temperature can be obtained by taking the anti-log of that, and we obtain that the total received noise temperature is 2610 Kelvin. We assume that the antenna noise temperature is 400 Kelvin, and the total noise temperature for the system is the sum of these two, which is equal to 3010 Kelvin. Now the noise is related to the effective noise temperature of the system through the Boltzmann's constant, and since N0 is in dB watts per hertz, we don't include the bandwidth. So if we express the noise in dB watts per hertz, then we take the 10 log of the noise temperature of the system and we subtract Boltzmann's constant in dB, and we get the expression for N sub 0, the one-sided noise spectral density. So the noise power would be equal to the one-sided noise power spectral density times the bandwidth, which is 20 megahertz. But since we're expressing it in dBs, multiplication then becomes addition, and we get the expression shown over here. And if we plug in the numbers, we get that the noise power is equal to minus 120.8 dB watts. And if we express it in dBm, or dBs of a milliwatt, where we subtracted 30 dBs. Now if we go back to the table for the sensitivity for 802.11a, we obtain that at 54 megabits per second, our received sensitivity is minus 65 dBm. That's the input signal power at the sensitivity point at 54 megabits per second. This is shown here. So at a data rate 54 megabits per second, our minimum sensitivity is minus 65 dBm. So the signal to noise ratio is equal to the signal power in dBm minus the noise power in dBm. So we have minus 65 dBm minus the noise power in dBm, which is minus 90.8 dBm. So we obtain for the signal noise ratio 25.8 dB. However, this was for a bandwidth of 20 megahertz. If we actually use the bandwidth, which is 16.5, since we're doing filtering, and we can filter out the guard intervals, so we can take off 0.835 dB off of the signal to noise ratio calculated at 20 megahertz, and we obtain the final signal to noise ratio for 54 megabits per second to be 24.96 dBs or 25 dBs. Now in a digital communication link, we are interested in the EbN0 ratio, the EB over N0 ratio, where EB is the energy per bit and N0 is the one-sided noise power spectral density. If S is the signal power, then if we multiply the signal power by the bit time T sub B, we get the energy per bit, and TB is equal to 1 over the bit rate, R sub B, so EB is equal to the signal power divided by the bit rate. The total noise is equal to the one-sided power spectral density of the noise times the bandwidth W. And the purpose here is we are going to relate EbN0 to the signal-to-noise rate. So if we take the ratio between EB and N0, then we can express EB as S, the signal power, times T sub B divided by N0 is equal to N over W here. We replace T sub B with 1 over RB, and we get the following expression for EbN0, which is equal to the signal-to-noise ratio times the bandwidth divided by the bit rate, R. So this is a very important relationship which relates the signal-to-noise ratio and bandwidth and bit rate to EbN0. EbN0 is used in the plotting of the bit error rate versus EbN0 in order to compare the performance of various modulation schemes, and we will show that in a minute. For OFDM, the bandwidth W equals 16.5 megahertz, and the bit rate at 54 megabits per second is of course 54. So W over R is equal to minus 15.15 dBs. And we already obtained the signal noise ratio at 54 megabits, which was close to 25 dB. We subtract 5.15 and we obtain 19.8 dB for EbN0 for 54 megabits per second. Here's an interesting table from IEEE 802.16a for OFDM mode, in which for various modulation schemes and code rates, the EbN0 is given in dB and also the received SNR in dB, the required received SNR. So at 64 QAM, the EbN0 is equal to 19, and the signal noise ratio at 3 1/4 coding rate is 24.4 dB. Both these numbers are very close to the numbers that we obtained in the case of 802.11a. Notice that the requirement is that the bit error rate be below 10 to the minus 6. That's very important. Anytime you define signal to noise ratio or performance, you have to either give the packet error rate or the bit error rate. In this family of curves, we relate the bit error rate to the value of EB over N0 for various modulation schemes. This family of plots is obtained from Proikis' book on digital communications, McGraw-Hill, 1983. We show the probability of error curve for QAM or phase shift keying at m equals 4, which they're equivalent to each other. So this is QPSK. So this is the curve for QPSK. And very interestingly, of course, and as expected, we get that the bit error rate at EbN0 equals 10.5 dB. We get a bit error rate of 10 to the minus 6. Let's go back to this table here, and you see that for QPSK at a bit error rate of 10 to the minus 6, the EbN0 is equal to 10.5. So that's why it's very important to relate performance to EbN0. We also note that at 64 QAM, this point over here, the value for EbN0 at 10 to the minus 6 bit error rate is around 20 dB, which is close to the value we have over here. And we also see that very obviously from these curves that there's a almost close to a 10 dB performance gap between the using QPSK versus 64 QAM. That is, 64 QAM requires a higher signal to noise ratio to achieve the same bit error rate, which is of course expected. So to summarize, we have given an overview of how to calculate the signal to noise ratio at the input of the analog to digital converter based on the noise figure of the analog front end, the RF receiver, and we've also related signal to noise ratio to the EbN0, which is a very important parameter in determining the performance of digital communication links. We have also shown and discussed some of the trade-offs in designing the analog front end versus more complexity in the digital baseband processor, especially where it concerns receive sensitivity, and the fact that we should strive to achieve very low noise figure in the analog RF front end in order to relax the requirements for the baseband digital signal processing. And even if you had the best performance in the baseband digital signal processing, the analog front end impacts the overall receive sensitivity in a dramatic way, so that we can always strive to reduce the noise figure at the analog front end.